Due to technical difficulties, a portion of this presentation was not recorded. We are joining the program already in progress.
The results here are mostly from an out-of-the-box configuration and with the release version of Vista, the one they call RTM. And full details of this paper or full details of this project are available in a paper, which is available on the Symantec website. It's also on the conference CD. Okay, we also looked at the security implications of Teredo. Teredo is a genus of shipworm, and although shipworms are called worms, they're not really worms, they're really mollusks. And there are some significant security concerns if you have a wooden boat or piling and so forth. That's because they could bore holes in the wood. So you need to watch out for that. Okay, the other Teredo that the project was actually on was a platform-independent analysis of the security applications of Teredo. This is an IPv6 transition mechanism for tunnels that tunnel through NAT. It is enabled by default in Vista. And full details of this project are in a paper which is on the conference CD and also on the Symantec website. Okay, I'm going to organize this talk as follows. There's first I'll talk about Vista's new network stack and firewall. You go into some of layer 3 and 4 results. Then specifically I'll go into the IP and TCP reassembly behavior. Then I'll go into the Teredo protocol, the background on it and how it works. Go into some of the security applications of Teredo. If time permits, I'll talk about LLTD. Then I'll wrap up. Some of the differences in Vista's networking that I'll discuss today is that the stack is a rewrite. IPv6 is enabled and preferred by default. This IPv6 transition mechanism is present. There's more tunneling mechanisms than in XP. There's the new Windows firewall. IP and TCP fragment reassembly is different. There's other different stack behaviors and other new protocols and exposures. When you have these new protocols and behaviors, these have implications for security devices, and they should also influence enterprise security policies and controls. I'd like to say that Microsoft loves IPv6. They've had this document titled Objectives for IPv6 up on the Microsoft website for a few years, and that lays out why they love IPv6 so much. And the main thing is that the global addresses and the absence of NAT means that peer-to-peer and games are easier to set up. The TCP/IP stack was rewritten in Vista from the ground up. This is at least partly to support IPv6 fully. And IPv4 and IPv6 are fully integrated in this stack. And as mentioned, IPv6 is enabled and preferred by default. So IPv6 is here. IPv6 has a number of positive and negative security implications. The list I have here, actually, all these were developed a couple years ago, even before Vista at all. And so these apply in general to IPv6 implementations and installations, and hence they apply to Vista environments. One of those security implications is that the possible attack surface is roughly doubled. That's because you have the IPv4 avenue of attack and the IPv6 avenue of attack. So it's twice as much as you need to protect. And I wouldn't say twice as much vulnerability possible, but definitely increased. Another thing is that the network security controls may not be ready for IPv6, and even if they are, they may not be configured properly, just because it's so new, and in fact there's less best practice available. You may not have turned on the firewall for IPv6 as well as IPv4 for a certain role. Another thing is that there's new, less tested code that will be present in stacks and in applications. IPsec is a standard part of IPv6, so you have the encryption and authentication available, although there's challenges to actually using it. Blindly scanning of internet addresses is generally infeasible, though there is other methods of host discovery. And tunneling raises security concerns. Okay, this rewritten stack means there's lots of opportunities for new vulnerabilities. Stacks are complex entities. They take typically many years to mature. There's thousands upon thousands of lines of code. So there's just lots of possibilities for things to go wrong. And Microsoft did do extensive security design and testing on the stack, and that has certainly limited a number of possible vulnerabilities. And in fact, in a beta 2 build, we did find three historic well-known stack attacks, like the land attack, and 3 crashes just from simple IPv4 fuzzing. So you make your own judgments on that. This is in beta 2. There's a number of new protocols in Vista. I'm not going to try to read the full list here. So there's new protocols, and there's a number of ones that are also re-implemented. Okay, and because Microsoft loves IPv6 so much, they want to promote more clients to be able to use IPv6. They've implemented a number of transition mechanisms, including ISATAP, which is IPv6 tunneled directly on top of IPv4, Protocol 41, and Trito, which is IPv6 tunneled on top of UDP on top of IPv4. These mechanisms can allow hosts to use IPv6 even if something on the path to your peer, IPv6 peer, doesn't support IPv6. So they do that by tunneling. Just as a brief background, the IPv6 header consists of a simple base header followed by 0 or more extension headers. The defined extension headers include hop by hop, destination options, authentication header, ESP, fragment for fragmentation, routing for source routing, and a mobile IPv6. And all but that last one are supported by Vista and any IPv6 implementation. Now I'll talk about what we found about this new firewall in Vista, just based on a kind of a limited study that we did. The firewall is enabled by default, and it does default deny, and there's fairly limited exceptions initially. In Vista, there's this concept of a profile that each network is in, and the 3 built-in network profiles: public, private, and domain. And what this profile is used for, among other things, is that it selects what rule set is in effect in the Windows firewall. Now, Ollie and I did find a vulnerability in Windows Vista in the firewall specifically, and we reported this to Microsoft. Sort of by design, what was supposed to happen is that inbound traffic over Trito was only allowed when there's a special flag set, edge traversal, in an active firewall exception. And since there isn't any exception like that initially, nothing was supposed to be allowed inbound over Trito. That's not quite how it got implemented, though. Somehow in Mr. Testing as well, is that the firewall allowed over Trito anything that would be allowed from the local link. Oops. The exposure depends on the current firewall rule state, but sort of for out of the box and for TCP, it meant port 53 or 57 was available from the internet over Trito. This was fixed in Microsoft's MS-0738, and we documented this in the Semantic Security Advisory as well. You can read the advisory for more details on this. We also wanted to find out how certain GUI actions in Vista affected the Windows firewall and the active sockets. For example, what happens if you turn on file sharing, turn it back off? What we observed is that certain features, when they're turned on, they create exceptions in the firewall. After consent prompts. But then you turn off that feature. Those exceptions don't always go away. These leftover exceptions even persist across a reboot. And thus, a legacy of firewall exceptions builds up until it's manually disabled. You have to go manually check them off. Here, this is just lists some of the things we found for the sticky rules. Actually, I think this lists all the ones we found in our limited testing. For example, you turn on media sharing, turn it back off. Well, the Windows Media Player group is still the exceptions for those is still there for the private and domain profile. So these sticky rules increase a host exposure, at least in theory, at least. Because it's lowering the defense. But of course, you actually need an active listener, to really connect in. And generally, the sockets did closely match the GUI state. We did find one small exception, though, is that you turn on Windows Meeting Space and then turn it back off. We did find that port 5722 was still available for an extra few minutes, just a couple minutes. So it isn't that great of exposure, but it's a little bit interesting nevertheless. Okay, now going to some of the layer 3 and 4 results. One of the first things you might do is when you have this new network stack that you're presented with is to do scans and protocol enumerations, and that's what we did for Vista. Looking at doing an IPv6 protocol scan, which is actually called NextHeader, is the name of the field in IPv6. We found that most of the protocols would produce a parameter palm message about an unknown protocol, which meant we can map which protocols appeared to be serviced. However, with IPv4, when we did the protocol scan with Vista, that with the firewall on, we didn't get any protocol unreachable messages. So just for the sake of seeing what's intrinsically available, we tested with the firewall off as well. These first results I list here, TCP, UDP, IGMP, those are pretty much what you expect. And we did find that ESP and AH, which are for IPsec, are available in both IPv6 and IPv4. Now in IPv6, these are extension headers, and there's 4 other extension headers, which I mentioned earlier, that those were present. But one surprising thing, though, is that right here, protocol 43 and 44 showed up as available over IPv4. And that's weird because those don't have any defined meaning under IPv4. For IPv6, they're fragment and routing. Now, is this usable or useful to attacker? And is this some way to do fragmentation or source routing over IPv4? Well, maybe. We didn't actually test it, but it points to something that's possibly interesting. And certainly inferring meaning from the lack of a protocol unreachable is not reliable. The lack of a negative doesn't establish a positive. Although like in certain beta 2 builds, an IPv4 packet with protocol 43 would cause a blue screen of death. And IPv4 packet with protocol 44 would cause some other different problems on the network. Now, there were some other protocols that showed up as available. These were associated with tunneling. And based on the IP scans, it looked like IPv4 over IPv4 and IPv6 were available. IPv6 over IPv4 and IPv6, and GRE over IPv4. But we didn't actually investigate the availability of most of these. But this is what appeared to be available. And there's a couple other tunneling mechanisms that we know of in Vista, Teredo and the IPsec tunnel mode. And this means that there's more tunneling available in Vista and then XP. And this is an area of concern due to the possibility that security controls be bypassed by this tunneling. The security controls, security devices don't know to look inside for the real content. And we do know that on Vista, the Teredo component will refuse to start up unless there's an IPv6 firewall in place. So that's a sensible security precaution. Make sure there's a firewall there. And there may be the same safety check for IPv4 over IPv6. And that's because of this right here, is that IPv4 over IPv6 only showed up when the firewall was on. It didn't show up when the firewall was off, which is kind of the opposite of what you normally expect because the firewalls do filtering. So that's one possible explanation as to why we get that result. Okay. Already did that one. Okay. We did a TCP port scan as well, and when you do the port scan, you might get different results depending on where the scan is coming from and what the network profile is. Coming from the same subnet with the private profile, we found that almost all ports were filtered. We didn't get any SYNACs, we didn't get any resets. Although one port, 5357, corresponds to web services for devices, was available over IPv4 and IPv6. We're able to connect in. Web service devices is a way for devices on the network to find Vista and to communicate. Incidentally, we did get the same result from the Teredo interface scanning from the internet. That's prior to the fix that Microsoft did. We also did a UDP scan, and we found that for all ports, we didn't get any response, which means it's either filtered or open. There isn't any protocol independent way to tell the difference between open and filtered under UDP. But based on just this firewall rule state and NetStat, the protocols I list there may be available. Okay, one of the things we ran into is that Vista rate limits ICMP v4 and ICMP v6 error messages to something like no more than 1 second, which means we had to slow down our IP protocol and UDP port scanning. And that's because those depend on seeing each and every ICMP error message that's produced. If you can't do 2 probes because you'd at most get 1 unreachable message back. And this meant it took us 18 hours to do a simple port scan over all ports. So this will slow down legitimate and malicious scanners unless there's some way to work around it, such as using multiple sources, say. Just a few miscellaneous observations from Vista. By default, does not respond to pings, unlike XP. Although if you turn on file sharing, it will. The IPv4 ID range, Vista only uses half of it for some reason or other. It only uses 0 to 7 FFF. I think I did one too many Fs there. And it does use the range sequentially, so it still should be possible to do host counting behind an AT. And the firmware port range has changed. The default is 49152 to 65535, which is different than XP. You can change that manually in NetShell. Okay, and now we'll go into some of the what we found from IP and TCP segment reassembly. Just as background for those that aren't familiar, it's possible, though not legitimate, to send an ambiguous sequence of IP fragments or TCP segments. For example, you send this different data for the same part of the same packet. Send it in different fragments, and the different TCP IP stacks will interpret these in different ways. That's because the TCP IPv4 or IPv6 specifications say how to treat these. But I remember being specifically disappointed that the IPv6 specification, when I read it for the first time a few years ago, didn't say what to do with these kind of packets. It left the ambiguity in there. And this creates a challenge for IDS and IPS that are network located, since those need to predict and match the behavior of the recipient system. Otherwise, it could be analyzing something entirely different than the recipient scene. So it needs to look at it to avoid evasion. And for more information on this type of attack, you can read the classic paper by Thomas Ptacek and Tim Newsham. Just as an example of this ambiguity, here's there's 4 overlapping TCP segments, and they're the data doesn't always, the content doesn't always match up. And for Vista, we'll say think this says this is bad. XP will say that is bad, and Linux will say that is mad. So there's an example of three different ways to interpret the same sequence of fragments. For Vista, we did an empirical analysis or empirical study of how this reassembly worked, and we found it is different than XP and other stacks. Old data is strongly preferred over newer data. This means that IDSs will have to adapt to prevent evasion. We also did this. We also did an empirical analysis for Vista and IP fragment reassembly. And again, we found that the behavior is different than XP or any other stack. And I guess this just goes to show that the stack is new. Although IPv4 and IPv6 will behave the same for Vista. Again, IDSs will have to adapt. Here's one example. You got 2 fully overlapping fragments, A then B. And in this case, XP and Vista will both prefer the old data, whereas Linux will prefer the new data. However, in a more general case, when there's partial overlap, the fragments don't line up neatly. In this case, XP will favor old, but Vista won't reassemble the packet at all. It appears that the state gets discarded. Although it is possible, though, for partial overlap to succeed, but the overlap must occur within the part of the packet that could already be reassembled, starting from offset 0. For example, here, when A comes along, B comes along, and those define the first 32 bytes of the packet, and then C comes along, which fits entirely within that. C, in this case, C just gets ignored. So this is kind of a weird shape of reassembly. It's not like a simple rule. And this, and I do go into more details on this in the paper. I present like 64 test cases that we did. And so it looks like this behavior isn't based on an intentional policy decision. It doesn't seem like that to me. It looks like it's just whatever the code happened to do for this case, and that means it means a couple things. One is that this behavior is more likely to change just with any update to the code, and also it means that Microsoft doesn't appear to have been aware of the issue for NIDS, or maybe they don't care. I think it's the previous one. They just weren't aware. Talking to an unnamed architect, from that team. That is what impression I got. It was just a casual conversation. Okay, and right slide here. Okay. Now I'll go into how we did our observations for the IP fragment reassembly for IPv4 and IPv6. IPv4 we took what's probably a classic approach, is in that the region that is fragmented ambiguously is the payload of a UDP packet. So then we ran a netscat as a listener on the recipient system. So when after the packet gets reassembled, if it will be reassembled, netcat will see the result. It'll show up there on the screen. And one of the things when you realize when you're coding the fragmenter is how do you set the UDP checksum, because you don't want to presume how the recipient's going to interpret the packet. And with IPv4, you can set checksum to 0, which means there's no checksum. That's your way around it. However, that doesn't work for IPv6, since with IPv6 the UDP checksum is now required. That means we had to develop a new approach. So for IPv6, we used the approach of sending a packet that, when reassembled, would generate an IPv6 error message. That is, we intentionally cause an error, but not until the reassembly completes. And that works because ICMP error messages will return the original packet. Well, in this case, the original packet is the packet as reassembled by the recipient system. And specifically, we used a destination option of type 9F. There is no such type defined, and that's exactly the point. And specifically, since it starts with binary 1-0, this the RFC for IPv6 requires that an error message be produced in that case. So that's how we ensured that we'd get the packet back, assuming that it gets reassembled at all. And this does take advantage of a new requirement in IPv6 that the full original packet must be returned, rather than just IPv4 is just only required that the first 16 bytes of the included payload or something like that be included. Okay, now I'll go into Teredo. Just a background on how it works. Teredo was developed by Christian Huitema of Microsoft. It was commendably brought through IETF. It was published as RFC 4380, which was a standards track individual submission. Some of the functional niceties of Teredo include that it works through NATs and with hosts possessing no public addresses. Does automatic tunnel setup. The Teredo client is provided with a global address and is globally addressable. No support is needed from the local network. That's because there's public Teredo relays and servers that are being used. The peer IPv6 host need not be aware of Teredo at all. And the local application need not be aware of Teredo at all. So it's all abstracted. It's transparent. Now, why is Teredo often needed for IPv6 connectivity? Well, it's a combination of three reasons. Many of the computers on the internet currently are behind IPv4 NATs, and these IPv4 NATs don't support native IPv6 or even ISATAP. And the fact that NATs, especially home gateways, are rarely upgraded, that means we're stuck with those for a while. So that's a major barrier to having IPv6, at least in some people's views. However, the specification does say that Teredo should only be used when IPv6 and ISATAP aren't available. That's because Teredo is less efficient and it's less reliable. It won't always work. I guess you could say that in general for IPv6 transition mechanisms, but I think especially with Teredo. And the phrase they use is that it should be an IPv6 provider of last resort. Okay, Trito is enabled by default in Windows Vista, and it is the IPv6 provider of last resort. It's not clear if it'll always be. There may be some cases where Trito is preferred over native IPv4. You got the tunneled version rather than just straight. And Microsoft hasn't really clearly documented this. So the safest thing to assume is that Trito will often be in use on just an arbitrary Vista host. So in fact, we did see it used more frequently than Microsoft's documentation suggested, at least what the documentation initially suggested. So there's some ambiguity there. It'd be nice if Microsoft clarified the documentation, made it more clear. Trito is also available on Windows XP and Windows Server 2003, although it is disabled by default. Okay, now I'll go into sort of how Trito works. There's this Trito component called a Trito server. I'd like to say that they're the client's helpful friends with the right connections. It's always nice to have those kind of friends, right? In this case, they have these native that these Trito servers have. In addition to having IPv4 access, they also have native IPv6 access. So that they can help out in that way. The Trito servers can help the client set up its address, the Trito address, and the server, among other things, the server will report back to the client what its external IP address and port is. It also helps the client determine if the NAT that it has is compatible with Trito. Many are, some aren't. In fact, Microsoft's implementation does some things beyond what the RFC says in order to try to support these other NATs. And Microsoft hasn't documented exactly what they do. The server for the client to use is generally statically configured on the host. That's the only part of Trito that's not entirely automatic. And for Vista out of the box, it uses some Microsoft servers that Microsoft decided to support Trito. They just wanted to stand up some servers to help. Trito addresses are IPv6 addresses. Whenever you see an IP address of 2001.0.0.0.0, that's a Trito address. I'm not going to go into the format in any detail, just in the interest of time. But these addresses are unique, and they are global scope, which means they're globally routable. Okay, just to sort of give an overview of how Trito looks on the network as it goes across the internet. Over here on the right side, where the single arrows, that's where the IPv6 is native, just pure IPv6. Although on the left side here, the double arrows, that's where IPv6 is being tunneled over UDP, over IPv4. Looking like this. Here's the real IPv6 content, and it's being included in an IPv4 and UDP header. And optionally, sometimes there'll be one or two layers of Trito data in between there. So that's what it looks like over on this side. These relays are here to do to interpret things the other way. When going in this direction, if I could draw an arrow there, it'll decapsulate the packet. It'll take it out of its IPv4 wrapper. And when it's going the other direction, it'll encapsulate it. And the way the relay can do that is actually kind of clever. Is that the Trito address has enough information for the relay to know how to address the client via IPv4. It has the destination address and the destination port included in the address. just because the IPv6 address is so much larger than the IPv4 address. And either the peers or the clients can initiate a packet send. It's pretty easy for the peer because it doesn't know anything about Teredo. It just needs to address something to 2001.0.0.0, whatever the address is. And when it gets to the relay will encapsulate it and send it along. And the way it finds the relay is that the relay is advertising a route to 2001.0.0.0. So just the normal IPv6 routing mechanisms take care of the routing. Now it's a little more work for the client. That's because it needs to find out what relay to use to reach a specific peer. So it gets some help from the server for this in what I call the ping test. Okay. How this ping test works is that the client creates an echo request destined for the peer, an IPv6 ping, and where the payload is a random number that it produces. The client will encapsulate this and address it to the IPv4 address of the server. When the server gets this, it'll decapsulate it and just drop it on the IPv6 internet. At this point, it's just a normal IPv6 packet. So that when the peer gets it, it'll respond to the ping, assuming it does respond to pings, and they'll get routed back to the Teredo relay. The Teredo relay will encapsulate it and pass it along to the client, and the client will verify that the payload matches. The payload is what they call the nonce. That's just to avoid spoofing. And the client will also remember that the IPv4 address and UDP port as the relay to use for that peer. And also, it's also only supposed to accept packets purporting to be from that peer if it came through that relay, or at least appeared to come through that relay. Now, you may notice a problem there in that some NATs don't accept packets inbound unless it's a recent outbound destination. But I'd say that's a sensible thing for NATs to do. So that the relay needs to work around this somehow. And Teredo does have a provision for doing this. That is so it can actually get past here. And that works through what they call using a bubble packet, which is just an empty IPv6 packet. The Teredo relay will address it such that it'll send it to the server, asking the server to pass it along to the client, and asking the client then to go back to the relay. Simple, right? So by doing that, the relay becomes a recent destination of the NAT, and then at that point, the relay can just directly send packets in. Just basically bypassing the NAT's restriction. And the server is always maintained as a recent outbound destination. Okay, now we'll go into some of the security implications of Teredo. Teredo does raise a number of security concerns, some of them serious, including unexpected host accessibility, the network security control bypass, the cost to locate the Teredo IPv6 payload, peer address disclosure, phishing and farming with Teredo. And there's several more that are beyond the scope of this talk that are in the paper on your CD. Teredo also does provide a few security positives. I'll grant that. And some of these concerns aren't mentioned in the RFC, Teredo's RFC. Because of this, I submitted a internet draft to the IETF to document our concerns. Now, this draft is now being maintained by Suresh Krishnan, and as of a couple of days ago, it has been taken up as a V6 operations working group internet draft. that's good. At least people are becoming aware of the Trito security problems. There wasn't really much documented before I started looking at this. One of the major concerns is that Trito puts hosts directly on the internet, by giving them global addresses, and anybody can send an IPv6 packet directly to the Trito client, and if the client's maintaining a stable open-ended tunnel. Now, just to be clear, IPv6 connectivity, end-to-end connectivity is the way it is supposed to be with IPv6. In fact, it was supposed to be like that with IPv4 as well. That's why you have global addresses, at least used to in IPv4. However, with IPv6, the administrators would certainly be aware of the exposure. That's because you set up your IPv6 access. Then you obviously think to have your security controls in place. But with Trito, especially on Vista, where it's enabled by default, I'm certain hosts will be unexpectedly exposed. Even if the administrator thinks so, they're just have a private IPv4 address, they're behind NAT, nothing to worry about, right? No. And other sides with Vista in particular, the Trito may often be active. The Windows firewall does default deny all inbound Trito packets, at least after that fix that they did. And Vista does require a IPv6 capable firewall to be registered before it starts up, as I mentioned earlier. Another major concern of ours is that the Trito's IPv6 content, bypasses inspection by network security components, such as firewalls and IPSs. And that is unless they are specifically aware of Trito and know to look for that content, inside of UDP. And this means that some of these network controls aren't being applied. And those are there for a reason, right? Some important controls may not be in place on the end host. They were on the network only, but they weren't available or put into place on the end host. And in any case, even if there's analogous controls both on the end host and on the network, your defense in depth is being reduced. This is a basic security principle there. And you should be applying at least as strong of controls to Trito tunnel packets as to IPv6. Okay, another major concern that sort of ties in with that the previous point is that inspecting all Trito content, either for selective filtering or passive monitoring, that's not trivial, and that's because only the server-bound traffic in Trito has a characteristic port, and that data isn't even the real data. That means you need to be looking at all UDP ports, all packets on all UDP ports. You need to apply a heuristic to find Trito packets, and that's expensive as it might sound. And so this may mean in some situations it's just so expensive that you can't do security inspection. Some devices just may not do it just because it's too expensive. If we think maybe routers or something. Although the situation for blocking just blocking Trito entirely is more tractable. That's because blocking outbound port 3544 should eventually starve normal Trito clients of their ability to connect. That's because it's blocking access to the server. That should work. The IETF seems to think it will. And I'd say eventually, because the effect isn't immediate. It only does that when the Trito client needs to verify its Trito address. So there may be a delay, and then it depends on whether the client insists on the server being still available. Although this won't, of course, prevent any kind of intentionally evasive type of behavior. But that's a hard problem to start with. Given this concerns about the selective filtering, this has recently seemed to motivate the V6 operations working group towards consensus that Teredo should not be used on a managed network. The latest version of the internet draft that I initiated says that Teredo is not recommended as a solution for managed networks. Of course, there's an internet draft work in progress. So that may not be the final language, but I expect that it will be. More poignantly, Christian Huitma, who's the author of Teredo, says that if an organization wants to provide IPv6 connectivity while monitoring IPv6 traffic, then Teredo is definitely not the right tool. So in other words, what organization doesn't want to monitor their IPv6 content? They say he says the best way to achieve this is by providing native IPv6, or at least using something like ISATAP instead. This was in a response to the V6 operations mailing list. There is some positive things from Teredo, in that the RFC does require a lot of sanity checking on packets that come in or are going out. Making sure that there's no encoded broadcast address, for example, inside the Teredo address. And that does prevent a number of attacks. And we verified that Teredo does at least some of these sanity checks. With Teredo, you can use IPsec in a normal manner, unlike with 624. And Teredo also specifies some decent anti-spoofing mechanisms to be used, such as the ping test. But watch out for a couple slides, though. And this is beneficial for when IPsec isn't being used for whatever reason. Now, how does this tie in for Vista? Is that Vista, at least as of release candidate 2, the nonce that's used for this ping test is only 32 bits long, whereas Microsoft's own RFC suggests that it'd be at least 64 bits. Don't ask me. I don't know. Also, sometimes 0 is used as this nonce instead of some random number, which we haven't dug into and we don't understand. Because 0 could be a random number, right? Yeah, you can't prove otherwise, right? Another concern is that the server knows all the peer IPv6 addresses. That's because it helps with the ping test, and that's fine if you trust that the server is not going to make any kind of bad use of this information. And did I mention that in XP and in Vista, by default, Microsoft servers are being used? Any conspiracy theorists out there? No, I'm just kidding. I think we could trust Microsoft on this, right? Yeah, another concern is what we call Teredo, the server bumping. The question there is, what happens if malware or some malicious user changes the setting for what Teredo server should be used?
Don't they own that server in that case?
Sorry?
Don't they own the server if they can do that? They just change your operating system. Just prove.
Yeah, but yes. Yeah, but assuming that somehow they do that, and they want to be subtle about it. Assuming this new server functions mostly properly, the user is unlikely to notice just because it's transparent. The new server could be malicious, and it could snoop what all your peer hosts are. There might be something interesting to like a jealous spouse or something. But it gets worse. if you ask a malicious Trito server to help you find a relay for an IPv6 peer, which is what you normally do for any new destination IPv6 address, the server could lie and say that it is the relay to use, or it could pass it along. It could have a friend's Trito server respond and say that it is the friend's Trito relay. Respond and say that it is the relay to use. And so there's various uses in this in fishing and farming. It just is another way to do farming. How much of this is a concern in the real world? It depends if the client prefers Trito over a native IPv4 address. But there's the potential, depending on the behavior, for the server to spoof all IPv6 capable servers on the internet. And as assigned for Vista in particular, well, the good thing is that you do need administrator privileges to change the Trito server setting. And administrator is definitely a lot less prevalent than in XP. And although if you do try to read the Trito server setting as a non-administrator, it'll always say that Trito.ipv6.microsoft.com is being used, regardless of the actual server setting, which is just kind of a quirk, perhaps having to do with the virtualization of DLLs or whatever. We haven't looked into exactly why it does this, but the implication is that it makes it easier to miss a bump server. So I'll always do this check as an administrator. Do the run as administrator when you open up NetShell. It also say that Trito is always not being used as well. My suggestions is that due to these security implications, we found for managed networks, I recommend disable Trito and block it on your network. Upgrade your security controls and postures to support native IPv6, and only then obtain an IPv6 connection, a native one, to the internet. And there's no way I have time for LTD here. You can, if you look at the slides, which I think it will be available, it's present there. Okay. Okay, so in conclusion, beware of Trito tunneling through your network. It may be imitating what the namesake mollusk does. See what you need to do as a result of these networking changes in Vista, and you can read our reports for more details. They're on the conference CD and on the web. Okay, at this point, I have 4 minutes for questions, I believe. Yes?
Isn't it true that a server on the host has to take special action to accept Trito traffic?
Server on a host.
The attack surface on the host is actually fairly limited because the service on the host has to opt in Trito traffic.
The Trito, well, it's up to the Trito client, and in Vista, the Trito client is enabled by default.
No, yes, you said the client itself could be exposing itself to attack. This would be potentially accepting Trito traffic, which would traverse the firewall. The fact is the servers on that host have to opt in and eventually say, I want to accept Trito traffic. And so that's
The server? Well,
find the socket, an IPv6 socket by default. I'm not going to get Trito traffic on that socket.
If you have native access to IPv6, no, but in general, if you just create a socket, the client will be transparent to you whether Trito is being used, at least on Vista.
Hopefully that's true.
Okay, you might be right. I don't know. Other questions? Okay. Any other questions? You can talk to me in the hall. Thanks for attending this presentation.